Hey guys, today we're going to learn about the complex plane. Now, in the past, we have graphed and you can plot points on the rectangular grid, also called the Cartesian plane, where you have your x-axis and your y-axis. Now, we can also plot imaginary numbers and complex numbers on what's called the complex plane. So in this case, the x-axis would be your real axis, and the y-axis would be the imaginary axis. These all represent points. So if I wanted to plot -2 plus 2i, that means that on the real axis is -2, and then I would go up to go for up the imaginary axis of 2i. So this would be A. B is 4 minus 4i. That means I would go to the right 4 and down 4. So right 4 because of the positive 4, which is the real number, and down 4 because of the imaginary number. Then 5 plus 3i would be to the right 5 and up 3. Now we can also work backwards, right? If you are given the complex numbers are graphed, then we can figure out what the complex number is. So here for A, it went to the right 4 and down 1. So this would be 4 minus I. B went to the left 4 and down 2. So this would be -4 minus 2i. Now C does not go left or right, so there is no real number. So therefore, this is a purely imaginary number. And since it goes up 3, this would be 3i. If you have your complex numbers are plotted, then you can also add, subtract these complex numbers. J is -4 plus I, and L is -2 minus 2i. So if I were to do J minus L, that is -4 plus I minus -2 minus 2i. So I would distribute this negative, and that would give me -4 plus I plus 2 plus 2i. And so that would give me, when I combine like terms, -2 plus 3i. Over here, k plus m. K is 1 plus 4i, and m is 4 plus I. So if I were to add, that's 1 plus 4i plus 4 plus I, which would give me 5 plus 5i. And finally, n minus k. N is 2 minus 4i. So n minus k would be 2 minus 4i minus k, which is 1 plus 4i. And here I would distribute the negative, and that would give me 2 minus 4i minus 1 minus 4i, giving me a result of 1 minus 8i. Now those are pretty easy to do, and another way of adding and subtracting complex numbers is by using something called the Argand diagram. Now the Argand diagram uses vectors to represent these complex numbers. So a vector is when you have, it looks like a ray. It starts with a point and then it goes to a head, which is like an arrow. So a vector essentially looks like an arrow. So how we do this, right? In order to graph A, which is 3 plus 2i, all of our complex numbers, or at least what we're adding, would start here at the origin, and then I would go 3 plus 2i, and this would be my vector. Then if I were to, I want to add B, I don't start from the origin again. What I do is I start from here, and I just do the movement depending on what B is. Since B is -1 minus 3i, this means that I would move left 1 and down 3. So from here, I'm going to go left 1, down 3. So that means that this here, from here to here, would be my second vector representing B. And my final answer would be from the origin to where B ends, right here. And so my result, when I add A plus B, should be 2 minus I. So now what we're going to do is we're going to do the algebraic analysis, meaning I'm going to take A, 3 plus 2I, and I'm going to add -1 minus 3I. And here I just combine like terms. 3 minus 1 is 2, and 2I minus 3I is -I. And you see how we end up with the same answer. So to break this down, the Argand diagram, I even put the steps here. You graph A with the tail at the origin. The tail is the first, like the end of the vector. And then graph B so that the tail of B starts at the head of A. This is the head. So we would start here, and then we use the movement of B to graph our next vector. And then C starts with the tail on the origin leading to the head of B. So essentially, when you use the Argand diagram, you should end up with what looks like a triangle. Let's look at a couple more examples of adding. We have A is equal to -4 plus 3I, and B is equal to 3 minus 4I. And we're going to use the Argand diagram to get our solution, and then we're going to confirm this answer algebraically. So A, remember, is going to start at the origin, and it goes to -4 plus 3I. So I'm going to go to the left 4 and up 3. So this is A. B is going to go right 3 and down 4. So starting from here, I go to the right 3 and down 4. So right here. That means that my solution, my final vector representing my answer, which is C, should be -1 minus I. And now we're going to go ahead and confirm that answer. So we're going to add -4 plus 3I plus 3 minus 4I. -4 plus 3 is -1, and 3I minus 4I is -I. And I have just confirmed that my Argand diagram is correct. Let's try that one more time. We have A is at -2 plus 2I. So I'm going to start from the origin, go to the left 2 and up 2. So this is A. B is going to go to the right 2 and down 6. So right here. So I end up with my resulting vector here going down the imaginary axis and ending right here. So this is my answer, which would be 1, 2, 3, 4, -4I, since there's no real number. And now we're going to confirm this answer. So we have -2 plus 2I, and we're adding 2 minus 6I. The 2's would cancel, so that's why we don't have a real number in my answer. And 2I minus 6I is -4I. Now, when we're subtracting complex numbers using the Argand diagram, we can't exactly use the same process. I mean, it is the same process. The only difference here is that instead of graphing B, what we would do is basically make it into a negative B. The Argand diagram only allows you to add vectors, not subtract. So what we do is we make B into negative B and then add them, because essentially that would be subtracting. So I'm going to distribute that negative, and therefore negative B is -7 plus I. And now I'm ready to graph this on my complex plane. So we have A starting at the origin. I'm going to go to the right 4 and up 3. So this is A. Now I'm going to graph my negative B so that it represents my subtraction. So it goes to the left 7 and up 1. So this is B. And so my final answer of C, which is my solution, is represented by this vector. And we can see that it is -4 plus 4i. And now we're just going to confirm. So 4 plus 3i, and then I'm subtracting b, so -b, minus 7 plus i. 4 minus 7 is -3. Oh, whoops, I counted wrong. 1, 2, 3. So this should be a -3. There we go. And then 3i plus I would be plus 4i. So the Argand diagram and the algebraic analysis should match. If it doesn't match, you always want to double check and make sure that something, that you just want to double check your answer. All right. Next one here, we have A is equal to -3 plus 2i and B is equal to -4 plus I. So since I'm trying to subtract, I'm going to turn this into -b, which would make it into a +4 minus 5i. A is at -3 plus 2i, so I'm going to go to the left 3 up 2. So this is my A. B is going to go to the right 4 and down 5. So this is B. And therefore, my final vector of C is this one right here, and it is represented by 1 minus 3i. And now again, we're going to confirm this answer. So we have A, which is -3 plus 2i, and I'm subtracting B, so +4 minus 5i. -3 plus 4 is 1, and 2i minus 3i is minus 5i is -3i. Now we're going to look at midpoint and distance on the complex plane. When you're trying to find the midpoint and distance between two complex numbers, first I'm just going to go ahead and plot these two complex numbers so you can get a visual. So z is at 2 plus 3i, so this is z, and w is at -4 minus I. So I want to find out what is this distance. Now you can find the distance either one of two ways. You can use the Pythagorean theorem or you can use the distance formula. Now the distance formula actually comes from the Pythagorean theorem, so regardless of which method you choose, you would get the same answer. Now I'm going to use the Pythagorean theorem because if I can graph it, it's much easier to work with. Now how this works is you can create a triangle based off of this diagonal. You can do a triangle this way or this way, it doesn't matter. So I'm going to create this triangle here. And what I get is a right triangle. And Pythagorean theorem, remember, only applies to right triangles. And how you find the distance, which is this diagonal, that is c, which is in the Pythagorean theorem as c squared. So here, your a and b, those are your legs. So we can find these lengths just by counting. So I have 1, 2, 3, 4, 5, 6 here, and 1, 2, 3, 4 here. So now I can find this distance. So c squared is equal to 6 squared plus 4 squared. 6 squared is 36 plus 4 squared, which is 16. So we get that c squared is equal to 36 plus 16, which is 52. And then I would square root in order to find that distance. So c, my distance, is equal to the square root of 52. But always simplify square roots if you can. 52 is when you multiply 4 and 13. And 4 can be broken down to 2 and 2. So this radical could be rewritten as 2 square root of 13. And this would be considered the distance of these two complex numbers. Now to find the midpoint is when you take, you're trying to find the middle of these two complex numbers. And how you do that, right, if you're trying to find the middle, that means that you're trying to basically find the average of these 2 points. So what that means is that you take both of the real parts, divide it by 2 so you can get the middle. Take both of the imaginary parts, divide it by 2, and that would also give you the middle, and that would be your complex number. So the midpoint would be, in this case, since z is 2 for the real part and w is -4 for the real part, we would do 2 plus -4, so -4 divide by 2. And then for the imaginary, it would be 3i plus -i, so -i, and divide by 2. 2 minus 4 is -2, and -2 divided by 2 is -1. 3i minus I is 2i, and 2i divided by 2 is just I. So I would write plus I, and this would be my midpoint. Now remember that we're dealing with the complex plane, so our points look like complex numbers. I use a comma to separate my work, but when I write my final answer, I do write my answer as a complex number because the midpoint is another complex number. And here I can check, right? -1 plus I is located here, -1 plus I. And you can see that it is pretty much, it's the middle of those 2 points. Let's try it one more time. Here I have that z is equal to -3 minus 4i. So here's z. And then I have w is at 2 minus I. So this is the distance that I'm trying to calculate, which is c in my triangle, because I'm going to use the Pythagorean theorem. And so I'm going to create here my triangle. I have this distance here is 1, 2, 3, 4, 5, and this distance is 3. So now I can create my Pythagorean theorem equation. 5 squared plus 3 squared is equal to c squared. 5 squared is 25 plus 3 squared, which is 9, equals c squared. 25 plus 9 is 34, and 34 is equal to c squared. And so when I square root, I get that c is equal to the square root of 34. Now, if you can simplify, we would, but 34, the only 2 numbers that multiply to give you 34 are 2 and 17. And we cannot break that down anymore, so there's no more pairs. So this is my distance, the square root of 34. Now let's find the midpoint. So for the midpoint, remember that you're going to take the real parts and add them and then divide by 2. So -3 plus 2 divided by 2. And then we do the same thing for the imaginary parts. -4i minus I divided by 2. -3 plus 2 is -1, and -1 divided by 2 is just -1/2. -4i minus I is -5i, and -5i divided by 2 is just -5 over 2i. So this is my complex number that represents my midpoint. And we can also check that, right? I mean, -1/2 is about right here, and -5 over 2 is about 2.5, which lands right there in the middle. And that's the complex plane.